pleasure to introduce Jeongwan Haah, Steve from Microsoft. And he will tell us about incompatible random walks.
Do you hear me? Oh, it's the speaker is on. Yes. It is my pleasure to be here. I want to talk about one of the recent results in collaboration with Chifang Chen, Jonas Happerkamp, Tony Matker, Yun Yu, and Xinyu Tan. So we're going to talk about complexity eventually, but let's start with the what's known, well, the basic knowledge. Let's just review it. Simple, fun, so let's do it. Sorry? We can hear you. We cannot hear you very well. Is the sound on?
Yes, it's on. Maybe just could be louder. Or you can speak up. Yeah.
Okay, I will speak up. So let's consider the set of all functions on the n-bit strings to binary valued. How many are there? The codomain is 2, the domain is that. So if you count them all, then it is doubly exponential in n. Now, that's really large number. But now instead, if you consider a circuit, well, on the classical bits, and you throw in some gates like AND gate or OR gate or NOT gate or here and there, and if you make a R of them, how many functions can we express in this way? Well, let's just count. How many bits do I need? Well, what information do I need to specify a gate? I need to specify where they are acting on and where the ending wire is going. And I may be using some ancillary wires too. You borrow some, you allocate some temporary memory and you use that. So if there are n bits in total, then each gate will be specified by specifying say 2 or 3 wires, some O1 number. O1 is because each gate is acting on O1 number of gates. And I may be using some ancillary bits for output. And output may be in multiple bits, but it will be O1 bit. So there's some polynomial of n and r. And each time I chose a gate, I don't have to worry about all the other. So overall, there will be a polynomial number of n and r raised to the power r. That's the number of functions you could possibly express by using r gates. And how do you compare this number to that double exponential number? If you only have a polynomial in many r, then the number is still far too less to compete with, to get anywhere close to that double exponential. This number r must be exponential too. So if you give me some random function chosen uniformly random from this, then almost always you will end up having a circuit that requires exponential number of gates. A simple counting argument. But now we want to think about a random circuit. We want to, well, ultimate goal is to lower bound a circuit. And what's the complexity? Complexity, by complexity, I mean the minimum number of R such that there exists some sequence of gates whose composition is the given function. That's my definition of circuit complexity that you could, you always deal with. Now imagine I have a function, well, a random function implemented by random gates. I chose, there are n wires going on, and then you tell me some random number, and I insert some random gate chosen from, say, 8 number of different gates, and I apply there, and I apply there, and so on. I keep doing this for R number of times. And then you ask, okay, you have implemented A instance of a random circuit. What's the complexity of this circuit? The upper bound is obviously R, because you have implemented exactly by R gates, but is that the best? Can you compress it a little bit? And this question, well, the obvious plausible answer is that the complexity of such a circuit R as a function of the initial chosen gates should grow somewhat like this. That's naive expectation. I don't think anyone else would doubt that. But somehow this question was not answered. The counting argument does not care about how I chose this. So this linear interpolation is a new question when you consider random circuits. And it has a relevance in the chaotic dynamics if you model a instance of chaotic dynamics as if it were chosen from a random ensemble. And you can ask about the growth of complexity. And the question is now, can you compress it?
Well, that's exactly that question, because I mean, if you look at the total set of all possible circuits, I think it's clear you kind of compress it, right? Because there's less parameters in the end, right? So
you are given one instance and then you optimize it. Can you do it?
Specific cases.
For specific cases. Well, yeah.
In specific cases, surely the answer is yes, sometimes, just not.
Yeah.
Right.
So
I don't quite see what the question is if it's not answered.
I'm sorry. So I said that I am choosing a random circuit, so the complexity will have some distribution.
Yeah.
Upper bounded by the linear. And how does this distribution look like? That's the question. Will it be something like this? Or will it be something like here, sharply peaked there, like that? So the generic behavior would be like this.
So the conjecture is that generically there are no shortcuts.
Right. Very plausible. Yeah, sounds reasonable. And when I first heard about the question, oh, how come it wasn't shown? So that's what we are going to talk about. Well, I mean, with this, what we are going to conclude at the end.
So then, is it, do you allow for small deviations, like some?
Yes.
Okay.
Yeah. Otherwise, well, in classical setting, it makes sense because the functions are discrete. But in the quantum case, it doesn't make sense if you don't allow such an approximation.
In both cases, or are you just doing classical?
Both. So let me give you in a two-sentence version. We're going to prove this by using unitary designs and permutation designs. So what does that mean? Before I get into all the various technicalities, let me just give you a working definition of a design. So for a classical circuit, I consider the permutation design, for which I mean the following. It is an ensemble of, it's a distribution over all possible reversible circuits, where the probability So if you give me truly random permutation out of permutation over n indices, then heating one particular permutation function for t inputs will be given by without this epsilon. The first, to match the first input, I need to have a 1/n probability. And since first one is chosen, and I'm thinking about the bijective function, then the next choice is now one less possibility, and so on. So this is roughly n to the minus t. And this is my working definition for permutation t design. I do not wish to motivate why do I care about this, but this is my working definition. And using this, suppose my distribution is a unitary permutation t design. Then can I say something about that complexity? Now, it is again a probabilistic counting argument.
Sorry, can you just explain that a little more? So it's XI or bit string?
Yeah, maybe right, XIs are bit strings, so.
The probability is over the permutation?
Probability is over the permutation group.
Yeah, it's permutations of the bit string, not of the bits.
Not of the bits, it's the permutation of the bit strings. So there will be a capital N elements in the the set you are permuting on.
Yeah, so XI, the I runs over independent samples. Sorry.
Sorry, I guess I didn't understand. I guess I didn't explain, sorry. So permutation T design nu is a distribution of the permutation group. And the requirement for it to be a T design in the working definition is that for any given permutation sigma, and for distinct bit strings x1 through xt, so T bit strings.
All sets of T bit strings?
No, just specific T.
Some particular.
Yeah, some particular T, chosen arbitrary.
T, but the bit strings are all bit string, all?
No. The bit strings are fixed. Bit strings are fixed, my sigma is fixed, and I want to match those, the image of the permutation, the image of the bit strings under the chosen permutation is matching the given one.
That's over average choice of bit strings?
Yeah.
Just a probability.
Also over the bit string choice?
No. So for a specific given bit string, you want to match the image.
Depends on which bit strings you pick.
The probability will depend on which bit strings I pick, yes, but I require that all of them are within this.
Has to work for all possible bit strings.
Yep.
Not on the average.
Yeah. So it is extremely stringent requirement.
So there's a for all XI that goes in front of it.
Yes.
Thank you, that's what I was.
Suppose my permutation, now my design is a permutation T design, and I draw samples from that to construct my random circuit, and I ask about the circuit complexity after R many of steps. Okay. But again, how many, so in the same counting holds up to, well, where's the formula? Oh yeah, this counting still holds. And if I only require the T images to be, well, the probability of matching the T images to be capital N to the little t, then the chance that my randomly chosen instance is describable by R or less circuit elements will be upper bounded by this. And this capital N was 2n. So in order for this probability to be appreciable, my R has to be at least T times N. So my my T design, my permutation T design has a property that if I chose R gates, then my circuit complexity is typically larger than T times N. In the unitary case, my working definition is the following. So I demand that if you give me a sample from my distribution, then I can calculate this expectation value. It'll be extremely small because of the exponent. But I demand that it matches the Haar random average up to multiplicative error epsilon. It's a very stringent metric. Again, you are trying to match the exponentially small in T number up to multiplicative error. It's like you're demanding a, some certain number of bits, how small the value is. And given this, you can do the similar counting, and now that expectation value gives you a bound on the
All fine,
sorry,
all fine.
for all phi, yes. Yeah, again, phi is playing the role of x over there. So this definition gives you a probability bound where the chance that your chosen unitary has an overlap with any fixed vector, high overlap, is very, very small. That's the working definition. And then it's a similar thing. So the probability bound coming from the working definition of T design gives me, if I chose a random instance for my ensemble, what's the likelihood that I will match a certain number of inputs? If I chose a unitary for my given ensemble, what's the chance that I will match the given vector in the very exponentially large dimensional unitary group? And that I demand that is pretty small.
What is big N?
Sorry?
Big N is 2 to the...
2 to the n, yeah.
Right. The lower board, I thought the lower board should be a consequence of the upper board.
Lower board is the constant. Yes, I said that.
It's not part of the definition.
No. That's the definition. This is a consequence. Yeah. And from this bound, by the same counting argument that you discretize the unitary group and that you apply the union bound, the chance that the randomly chosen random circuit has a complexity lower than R is going to be appreciable only if R is around T times N.
What the conditions are factoring the same, or do you have a fundamental normalization?
What?
Things are all smaller than 100.
Yeah.
Good.
Times. Yeah, yeah, board was a bit smaller. Yeah.
It's time for another discussion.
Right. So we could hope to prove this if we could generate a unitary T design or a permutation T design more efficiently. If the design property increases over time as we add more and more layer, then that will immediately imply by discounting arguments about the circuit complexity. That's just a proof tool. One may wonder if there's a shortcut. There may be, I don't know, but this is the only known method known. So now the problem moves on to designing a design.
So can you, before you do that, can you
Yes.
say in more detail why that would solve your problem?
No, it does not solve the problem. I'm just making a connection that to prove this, I will going to, maybe I.
Yeah, I don't see how you get a lower bound from having.
Okay, right.
A lower bound.
Okay. Suppose I have a random circuit of consisting of L gates. And then as a function of L, my distribution of the L number of random gates will define a distribution over the entire unitary group. And I ask, what's the largest possible value of T such that this defined distribution satisfies the definition of T design?
Yeah.
And suppose L gives me O of L, well, theta of L. It turns out that the parameter T can be as large as L.
Yes, you really need to show that this generic circuit is the T design.
Yes. Yeah.
I have a very elementary question. Are you choosing points at random on the book, one after the other, or is there some memory of where the previous point was?
No, it's a Markovian process.
So when you say random walk through the space, it's not like every step is closed.
I'll get to that point, yes. So I was going to show this picture a bit later, but let me tell you now. So the random walk. So when you consider a random walk, say on a circle, then you start with a point particle here, then you go either left or right, left or right, randomly, and then you have some diffusion process. Here, it's more of something like this. It jumps over all over the place.
It's not local in the group, but it's local in complexity space.
Exactly. Yeah. Right. So if the L gate random circuit gives me T omega of L, then I will just plug this in, and the complexity will be lower bounded proportionally by L. So that's the strategy. But let me show. Well, there are many metrics about the random walks, and to motivate the particular in that one that we are working with, I just want to digress to the heat equation. It's a heat equation. Laplacian Laplacian determines the time evolution of the distribution. For computer scientists, I'll get to the more familiar notion to you. by discretizing it. Well, that's what I'm going to do now. So what's a Laplacian? Laplacian is second derivative. But what's a second derivative? It is, if I have a for very small h, that's a second derivative for nicely behaving function rho. But if I imagine the function not to be continuous or anything, if I just discretize the domain, then this expression is like I take -2 of the function value at this point, and then I add another function point at the slightly on the right, and I also add another function point on the left, and that's going to be, and then maybe perhaps normalize it properly, and that's going to be my change in my function. That's what this heat equation does. Now, this 2 is actually the number of possible inflows to this point. There are two points nearby, and they are sending me something. At the same time, I am, at this one sitting at x, is sending something out. One to the right and one to the left. And that is precisely captured by the adjacency matrix of a graph. So, a graph is a tuple of vertices and edges, and the adjacency matrix, you put 1 whenever you see a row and column where the I and j are edge, and the 0 otherwise. So 1 means they're friends, and 0 means they're not.
What is I and j?
I and j are vertex nodes. So for a simple graph, this is a symmetric matrix, because if you are friends with other, then other is friend to you. And then my number of friends, the -2, is going to enter in the diagonal. So this is my discretized Laplacian. I'm using the minus version of what computer science talk about, but this is more direct analog of Laplacian on a graph. My degree is the number of things that I receive at a one-time step, and the adjacency matrix tells me where to go in the next step from me. Once you have a Laplacian as a
degree times 2.
No, just degree. There are 2 edges coming out of one vertex. That's 2. And once I write in this form, then what do I do? When you see a linear equation, the first thing you should do is to diagonalize it and look at the eigen vectors. For the simplicity, let's assume my graph is constant degree. So degree is a diagonal matrix with all the same entries everywhere. And then and there is an obvious vector in the kernel, all one vector. In other words, if rho is a constant function, it's the same everywhere. And if I sending one bit of heat, one energy unit to my friends, and then each friend gives me a 1 unit of energy at the same time. If it's a constant, that I don't change. So this is a constant function, and don't change means that the Laplacian must vanish, and that means this is an eigenvalue 0 eigenvector, which we are not very interested, by the way. And Laplacian is negative definite, semi-definite. So my Laplacian, either continuous or a graph, they're the same thing conceptually. It will have a spectrum, eigenvalue spectrum, 0, the obvious one. And there may be something here, and dot, dot, dot. The first non-zero value is the most important one because it means how fast my rho will approach the constant function. Everything else only accelerates that process. So the difference between the two values is called the spectral gap. Yeah, we're looking at the spectrum and the gap. And this determines the characteristic time of the decay process. At the end of the day, you will have a constant function. And that's exactly what we want. If you look at the working definition of the permutation T design or the unitary design, which I erased, it means that the probability, or you should think about the density function here. Probability density function is approaching the uniform function. So I want to reach there. But instead of writing down the explicit distribution, I want to, quote unquote, automate the process by introducing some heat equation here. And that's why we are interested in the random walk. You specify some local rule defined by this Laplacian, and then let the dynamics do the job for you. No. But for most nice graphs, it is unique. Well, as a trivial example, if you have two disconnected graphs, then the uniform distribution here is an eigenvector. So now we are well motivated to write down a quantity of interest. We want to study this spectral gap for a given Laplacian. And how can we express that? This is minus, and well, yeah, so the trick I use is shifted everything to the positive side, eliminate the top one, and read off the norm. So Laplacian, shift everything by the degree, degree identity, and then subtract the projector. So this is the projector onto the, this distribution vector of the constant function. The shifting by degree is just to shift every spectrum to the positive side. And this is my operator of interest. But this is nothing but just A. So adjacency matrix, subtract the projector onto the top eigenspace, and then take the norm. That's your spectral. Well, that's the parameter lambda. And the 1 minus of this value, that's going to be your spectral gap. So this is well-motivated quantity, more than anything else. Sorry?
Say 1 minus?
1 minus. Laplacian plus degree times identity minus projector onto the top eigenspace.
Let's see what's behind them.
Oh, yes, 1 minus this norm.
The largest, isn't the largest, shouldn't it be degree minus?
Degree minus? Yes. So let me normalize everything by degree. Yeah. Well, this is good. So we got the object of study, but we want eventually SU2 to the n. It's a continuous group. Laplacian on the SU2 can be studied and has been studied for small enough groups, but the topology makes us headache. It's too complicated. But now we have to look for another simpler analog. And for that matter, we should look into the Cayley graphs because SU2 is a group. So why not study the finite version first to find the relevant quantity to study? So to keep the talk most accessible, let me not assume that you knew about the Cayley graph. The Cayley graph is a graph, a simple graph, defined by a tuple, a group, and some subset. It has nothing to do with the group structure. It's a sum subset, a generating subset. So if you multiply enough elements from this generating set, then it becomes the full group. This is the vertex set. And the edge set is a collection of 2 points of this form. So give me a group element, and yes.
The degree here, we have to assume that the degree is the same for all the sides of the graph?
Yes. Yeah. You could play with others, but let's not make too much complicated.
And there's no relation between this and n. N is the total number of sides.
N is the total number of sides. Degree is the...
Say that n times the degree maybe over 2 is the total number of edges?
Degree times n over 2 is the total number of edges, yes. Yeah.
There's nothing to do with the other end.
No. Yeah, I temporarily digressed from all the stuff and just... Right. So yeah, group element, you shift, you go according to the description of S, and that's your neighbor, that's your friend. And for the simplicity, I assume that the set of inverse is actually the same as S. So it's closed under taking inverses. Then your friend, and you call someone friend, and someone will call you friend too. So in this set, what's the Laplacian? Well, I mean, you could think about gigantic matrix whose number of rows is equal to the group order. And then you write down, you fill out the entries here, 0 and 1s and so on. But it's, if we were going to do that, why do we study group? Group has a structure. We should exploit that. And the one observation is we are working with matrices. Matrices is supposed to act on some linear space. It's a linear map. But what's the relevant linear space here? We're implicitly taking the linear space of formal linear combinations of vertices. But vertices are group elements. So we're taking formal linear combinations of group elements. And that has a name, group algebra. So the agencies matrix is a linear map acting on the group algebra. And your neighbor, so how to find your friend? You are G, you are at G, and if you multiply S, then you go to your friend. So multiplication is a linear operation over the group algebra. So the adjacency matrix is nothing but the sum over all elements in my chosen generating set in the construction of Cayley graph. So that is precisely my linear operator, the adjacency matrix. And well, okay, so I got the first term. with a proper normalization, I have to divide by 1/degree, and the degree is equal to the number of elements in S. S tells me who to talk to. Oh, okay, so that's an average over elements in S, viewed as a group algebra. What about the projection onto the constant eigenvalue 0 thing? Well, if you ever studied the group representation theory, then that has a very nice description. Sum of all elements is invariant under all group action because it's sum of all. It's a uniform thing. So this is the projection onto the top eigenspace, and this is my adjacency matrix. So the quantity of interest for the mixing property of this Cayley graph is going to be this quantity minus this. So that is my interest. Okay, now I can go to continuous group. Oh, I chose some subset of my continuous group, and this is going to be a integral. But there's another problem. Viewed as a matrix, this is a size order G. If you go to infinite group, the matrix is infinite. I don't want to deal with the infinite matrices. So I want to make it finite dimensional. How can I do that? Okay, let's stare at it. Group algebra, linear operators, group algebra itself is a representation of the group. And the regular representation in the group algebra is a direct sum of all irreps with the appropriate multiplicities. It contains all possible group representations of finite dimensions. And continuous groups may have finite dimensional representation. Oh, okay. Now, instead of studying the infinite dimensional matrix, now we can study the finite dimensional representations of a given group and with a chosen subset of that group. And that boils down to the final quantity of interest. So that's the spectral gap for any distribution on any compact group where you can talk about the averages. So rho is any finite dimensional representation. The role of this subtracting term is to pull away the trivial subrepresentation part, and this is the adjacency matrix part, the Laplacian part. And this 1 minus this quantity tells me how fast the slowest rate at which my uneven distribution will decay into the even distribution. So this is a very well motivated quantity, and from the connection to the graph theory, if this quantity is positive, people call it expander.
So basically, you say you want to know this in female, but now you restrict to some finite dimensional representation of something.
Yeah.
But this will make your infimum larger, which is what you want. So what do you want? You want to upper bound the gap or lower bound?
I want to lower bound the gap, of course.
Then this will work. You take the infimum of a smaller type of object. You get that. A bigger number.
What?
You're missing a lot.
I'm just making a direct analogy from the the mixing property on any graph, and I applied it to the continuous group, and that's the most natural quantity that you want to study.
You could take the infimum over all possible irreps. Is that again the ideal?
Oh yeah. So of course you could study irreps. In that case, you don't need this, but the rho needs to be non-trivial.
That's a spectral gap of what?
Spectral gap of nu. So, well, I mean, when we talk about the graph and the adjacency matrix, we chose a certain subset. Implicitly, when we meant that, if you think about the heat equation again, I have two neighbors, and with the equal probability, I toss 1 unit of energy each time to the left and to the right. So every neighbor is equal. But to study the random walk, you don't have to do that. You could distribute, well, I like this friends more, so you toss more energy into that, and so on. Right? You could do that. So in the most general setting, you want to study a distribution over the group. It may be some average of Dirac functions. It may be some smooth distribution, but this is the most general thing you can write.
And where does the restriction to some finite dimension Dirac representation enter? So I think that's what's really confusing. Yes, so random walk on original group, right?
Yes.
So you want the infimum over the whatever full.
It's just a technical trick that I don't want to deal with the infinite matrices.
No, I understand. But
Yeah.
I think by restricting, you would think the infimum gets bigger, which is not what you want, right? That's my problem. I understand you can restrict it to some representation, but will you get the correct optimum?
That's a non-trivial.
Take a trivia here. Like you look at the very boring bound and you would
Yeah, that's a non-trivial thing, but there's a there's a good justification. The Hilbert space of L2 functions on a compact group is a regular representation. It's called a regular representation, and it is an infinite direct sum of finite dimensional Arabs with the appropriate multiplicities.
But you have to optimize over all Arabs.
Yes.
It's not that you pick some Arabs.
Right.
Okay.
Right.
So there's a second infimum over the choice of all Arabs.
Yeah. What? Oh, yeah. Maybe I missed. Yeah. Rho is an Arab. Rho is an Arab. Yeah. So that's the mathematical, quote unquote theory part. Does that have relevance to our complexity question? Yes.
Any sense that the graph is denoted of locality, or can we have edges between anything random?
You could study that. Well, that's more appropriate when you think about the Laplacian in a metric space. But here, we, in a sense, intentionally avoided that. We want fast mixing. If you restrict yourself to the new distribution to be like some point-like one, it will eventually converge to the uniform distribution, but the convergence rate may be very slow.
There's no sense of this approximation of some continuous space.
No. Yeah, that's a leap. Right. So now, coming back to, well, let's not forget about our goal. This is a mathematically well-defined subject, and there's books written about it. But we don't want to deal with the arbitrary Arabs. Maybe that's too much. So people implicitly have only focused on the Arabs of so that's the that's the only that's the only thing that is studied, and that's legitimate because the linear representations of the projective group is a sub-representation of for some t, so that's a reasonable thing to do. So let's apply that formula to this. Then the object of interest is now the expectation of
No is any set of group elements here?
sorry?
No is any collection of group elements?
It could be a collection of group elements or any distribution over the group. probability distribution.
Looks like it shouldn't contain the identity.
It may.
It's
That-
bound to contain.
Yeah, I mean, it hardly changes the picture. Yeah.
What we're looking at here though is averaging of the new minus the power average of this u times to u bar to the t.
Yeah. Sorry, what's your question? Sorry.
I just want to make sure I understand what you've written.
Oh, yeah.
The norm of the average of the new minus the average of the power measure.
Yes.
Of this expression.
Yes. Yes. So this is the projection onto the trivial subrepresentation. This is this contains all the interesting errors for us, and that's the quantity of interest. And this has some operational meaning. This, if you've written out all the matrix elements in the gigantic matrix, well, gigantic but still finite, it contains all possible monomials of the products of matrix elements of U. And I demand that, well, if this quantity is small or the gap is large, then that quantity is close to that of the Haah over the Haah measure. So you are matching the teeth moments overall. And that came from the, naturally from the connection to the, the mixing property of over the graph and Cayley graphs.
Sorry, can you repeat what norm this is?
Good question. So here we were looking at just the eigenvalue. So this is the maximum singular value, and that continues here. And yeah, this is that norm. Now, speaking of norm, that's the time to talk about various ways of talking about other metrics. There are many. So I I tried to find, but this norm quantity, I mean here, that didn't have a name, so we coined a term essential norm of nu. And then there is a associated quantum channel for any distribution. There is an associated channel very closely related to this linear map, and which is actually exactly the linear map if you think of this channel as a linear map in the space of density matrices. This is the place where density matrix goes in. And given the channel, you can think about the various norms put on top of it. So let me call this A, and people call it additive error for the distribution nu, always relative to the Haah measure. And there is something called multiplicative error.
That subscript in the norm?
Sorry?
That subscript you wrote on the norm, what does that mean?
Diamond norm. It's operationally defined. It's the maximum probability that you could ever distinguish the two by a one-shot experiment. It is infimum of epsilon. Oops. So, sorry?
On the right, you want R.
Yeah. Thanks. So multiplicative norm is, well, it's not exactly norm, but multiplicative error is defined to be the smallest epsilon such that this inequality holds, where the inequality means if you move this thing over, then the channel is completely positive. And this definition reproduces my working definition of designs that we started with. It's a straightforward derivation. And this is not a metric, by the way. It is not obviously symmetric between these two elements. So, but it is useful to talk about the complexity. So it is a one error metric. And there's another that is rather much discussed in the high energy literature. So-called frame potential. And that is, well, frame potential minus its Haar value is it's just that. So in a sense, yeah. So the difference between essential norm and the frame potential is that it's the same operator, but in the essential norm, you measure it to the operator's norm. Here, you measure it to a 2 norm and square it. So the square root of the frame potential minus its Haar value is a metric. And this is an abbreviation of what I wrote previously. Expectation value of the U tensor U bar raised to the power T. Yeah. And just for the, just give you this a flavor of how things may become not so beautiful. Let me give you the relations among them. So none of them are equivalent. The conversion almost always involves the dimension factor.
You say what M is?
Yes, M is this. Yeah. So, well, one lesson, if you don't want to look at this inequality, if anyone is 0, then the other is 0. If anyone is approaching 0, the other approaches 0. But often that is almost always useless because we want to control the value somewhere between 0 and 1, and the multiplicative factor of dimension is too large. So depending on the problem, you have to choose the right one. Arguing that, oh, one norm is small, therefore it is a good thing, that's too vague. You need to find an application to justify your choice of error metric. So in the recent paper, one of our contributions is this inequality. Yeah, this is one very useful lemma. The essential norm is upper bounded by the additive error if the nu, the distribution of u itself according to u, nu versus the distribution of u dagger according to nu is the same. So in particular, Haar measure is S alpha adjoint, and almost all distribution you want to study will be S alpha adjoint. So in that case, this holds. Naively, there is a dimension vector, like here. No, right? If you combine this and this, then there is some polynomial factor in N that upper bounds the essential norm by A, but you can just bypass all the dimension factor. And that was actually crucial for the lower bound to make it linear.
Then it's not bounded by A.
No.
Is it
No, well, no, I mean, I don't know.
is it a passive node? A is basically a one norm of the choice state,
Uh-huh.
the thing is operating
Yeah.
the choice state.
But we didn't spend too much time finding a counterexample. Yeah. Okay, so now I can state the main theorem. So those two statements are the result. We give some explicit exponent, but that's not too important. So let me just explain this. This is a distribution obtained by picking up random 3 bits. There are n bits, you pick a 3 bits, and then you apply random permutation on that 3 bit. So you apply a random element from the symmetric group of index 8. And once you do that, then the essential norm is that much. And this one is a quantum version. You pick a 2 qubits at random, and you apply a random unitary from the SU4. Then basically inequality holds. The key point, the upper bound, is independent of t. Here, it's mostly independent of t, but up to that value. It is somewhat unsatisfactory, but we couldn't get away with that.
Sorry, what should we conclude from these bounds? And maybe we'll get to that later.
Right. So as a corollary, what?
You still be far away from Haar.
Oh, yeah. Right. But remember, this essential norm is the spectral gap of the random step, right? But who told you you have to go only one step? You could go many steps. And every time you go one more step, essential norm decreases exponentially. Well, the essential norm is the base of that exponential decrease. Yes. I mean, if you think about the heat equation, then that's natural. This is the decay rate. You just increase the time. So the corollary is Um, uh, so if you go to L step, then the design parameter T that controls basically measures the evenness of your final distribution to the Haar measure grows linearly with that number of steps. This is a fixed polynomial, and this bound applies all the way up to this value. So by the previous counting argument, which was erased, the complexity grows linearly with allowing room for small error. The upper bound is strictly linear. And the lower bound we give is like somewhere here. And the gap is all the end. But the whole argument just breaks down when when your number of steps is larger than 2 to the n over 2. So we have nothing to say in that regime. And that is somewhat expected. There are two sources of this thing. I mean, eventually after exponential time, you could reach anywhere in the unitary group. So complexity should not grow after that. So your argument must break down at some point. But whether it's a 2 to the n over 2 or 2 to the n or 4 to the n, that's probably an artifact of the analysis. But my guess is that the complexity should grow all the way up to 4 to the n. But that's the status. In a little bit more detail, there are two places where this breaks down. One is the counting argument. The counting argument breaks down at the 2 to the n point. And our spectral gap analysis breaks down after 2 to the n over 2. Counting argument could be pushed a little bit, I think, but we didn't try because much earlier, anyway, the argument breaks down. There's no reason to push forward on that counting side.
Sorry, there's a last step of this argument that it's probably trivial, but I just haven't quite processed it.
Yeah.
So, let's take this result. So then, but now I claim that nonetheless, there's a shortcut.
Yeah.
I mean, what if the shortcut is just also a T design? I mean, I don't know. Yeah, like how does this rule out that there's not?
No. So the complexity is proportional to the design parameter T by just counting.
Why?
I didn't show the counting with you, but it's not that complicated. Basically, the definition of T design I am using is using the multiplicative error. And the T design reproduces the expectation value of some very tiny parameter up to multiplicative error. And that gives you a bound on the volume of the states that are close to a given one if you chose randomly. So it's very stringent requirement. Yeah. So well, so coming back to your very first question, I think. So what we show is not exactly the straight line, but more of a distribution that initially it's it's fuzzy. We don't really care, and as you increase the number of steps, the distribution of the complexity as a function over the random choices is becoming sharper and sharper. And the midpoint, the average value, stays within this small window. I could spend some time explaining Well, let me spend like 5 minutes. Yeah.
So this poly n, do you have bounds on what polynomial is it like? Do you have explicit expressions for
Yes.
what polynomial this is?
Yes.
So what is
Like n to the cube or n to the fourth. Yeah. Something
okay, so that means that we have to do more than n to the 4 steps.
Yeah.
To be
meaningful. So it marginally suggests that, oh, there could be some polynomial factor compression for an exponentially long deep circuit, but I don't think it's likely. Maybe it's just an artifact of analysis. So by the way, the unitary random circuit complexity stops, well, I mean, our bound stops at 2 to the n over 2, but the classical side, the complexity of a reversible random circuit, Toffoli gates, basically, that grows all the way up to 2 to the n. So there, it is best possible, basically there. So how do we show this? We were lucky at least at 2 points. In February, there was a so-called PFC ensemble was analyzed, and they gave a design bound in terms of the A, the additive error, and we found the conversion to the essential norm. That was one thing, but the existence of such a nice-looking ensemble was very helpful. And the second is another luck for us. Martin Kasabov around 2004, 5, 6, he gave a theorem, which itself is quite amazing. So for all n, there exists S, a subset of alternating group of n elements, such that the number of elements in S is like, I don't know, maybe 10 to the 10, a fixed number. And in the spectral gap essential norm of the Cayley graph of this alternating group with respect to this S is upper bounded by 1 minus, I'm cooking up a number, say 10 to the minus 100. Some small number, but independent of anything. If you think about it, it's amazing. This is gigantic group. It's an n factorial number of elements out there. You only chose 10 to the 10 friends, a constant number of friends. And then if you talk to them, then they will spread out your message all over the place at the rate, fast as possible of the constants.
These constants enter your poly n in some way?
No.
No. So
no.
is it
Sorry?
nice or is it something powerful about poly n?
No, it's all buried in the constants. So, when in that sense, yes, it enters in the poly n, yes. Yeah. But Kasabov's paper did not discuss the efficiency. So he gave a pretty explicit generating set. There is a very explicit set of those 10 to the 10 elements. But if you give me some random elements in the alternating group, then I will typically have to spend exponentially many gates to implement each. And how I will not be able to use that in this, more or less efficient random circuit. But we found an efficient implementation of each generating set, and it turns out every generator has only order n gates in it. Yeah, if we were not told about this reference, then I wouldn't be able to say that the complexity grows linearly. And the third ingredient is a more of a mechanism rather than a lemma. Well, you could call it melting or composting. So the unitary design obtained by this has a step where it is highly structured. It's not just that you randomly apply a one gate. It's more of a, oh, you go to, you drive 10 kilometers, 10 a fixed number, but you make a right turn there and left turn there, and very specific thing. But we have to decompose all those specific directions into a random choice. And there we go back and forth between the various distributions. It is a bit of gymnastics, but we managed to do that. And the polynomial factor, the hidden polynomial factor here, that's the result of that gymnastics. But gymnastics wasn't exponentially long. That's why we end up with a polynomial. Yeah. Okay, thanks for listening.
Does additive error design imply complexity?
Not that I know of. You would incur another factor of t. So if you're only given additive error t design in a linear depth, then your lower bound will be a square root.
So how do you connect your result now to this very first line that we wrote there, this Shannon's result of 2 to the 2 double exponential?
It's an interpolation. So Shannon's result has nothing to do with the gradual growth of complexity. It just says, if you give me a random a function, here random means that one out of all possible functions without a specific ordering or preference, then it is typically hard to implement. And the bound is uniformly exponential. But here we're talking about the growth of the complexity. If I implement a random unitary here and another unitary there and so on, then you ask, given instance, how complexity as a function of this number of steps grows. It's a different question. And in a sense, it matches. It grows all the way to the exponentially long deep circuit.
If you choose a random qubit gate and then you iterate it, but it's always the same one.
Oh.
Although like a unitary circuit with a complicated Hamiltonian.
Right.
Also bound in that case.
I think it's going to be hard. Well, you can imagine, well, if you were applied the similar technique here, then almost certainly that wouldn't work. It's a random walk that, we started with identity. It's a delta function initially. And then due to this random walk that jumps around the whole Lie group, it just generally spreads out. But what you're saying is that I fix, well, not exactly the same, but it's very similar to, you fix a random direction, say, your Hamiltonian gives me a direction in the Lie group. And then you follow that, and you hope that every point complexity grows as linearly with the distance from the origin. I would believe it, but proving it is a completely different matter.
In the probabilistic literature, there are something called mixing time. So sometimes, for a Markovian process, there's a critical time that you do not mix, the norm doesn't collapse, and after some critical time, they collapse abruptly. So is there any geometry of circuits also behave such a mixing time? So or is it generally always the T design always increases? The T increases as you increase your L. Is there any examples of?
No, I don't know any example, but the analysis does not rule out that scenario because, you know, in order for this to be an appreciable number, you have to walk at least polynomially many steps. And that's the starting point at which this bound becomes meaningful. And we don't know what happens before that.
Oh, it's time to thank the speaker again.